people, today's topic is rational function, and let's look at the definition of the rational function first. Rational function, when you say a rational function, it means a function that can be expressed in a ratio of two polynomial expressions. Let's say there's a polynomial f of x and polynomial g of x, and if they are in ratio, you can say that it's a rational function h of x. It's that simple. And let's get right into how to deal with the rational functions. This is the standard form of the rational function. You can see several factors included in this expression. And let's look at the first two factors you can see. The first factor is a, which affects the value of function overall, except the k. So it's going to affect the value of y, which makes it to be a factor for the vertical stretch. In case of the b, b is affecting the value of x, and that's why it's going to affect the horizontal stretch. And the other two factors, k and h, it's just same as the other functions. When you're dealing with other functions, you also see the translations, and just subtract the value of the I'll show you an example. That'll be a better explanation, I think. Let's say you move a graph by 5 units in a positive direction in x, and you move 7 units downward, negative 7 units in direction of y, and that's going to change the graph of the function a little bit, because in the place where x was, there's going to be x minus 5 instead of x, and in the place where y was, there's going to be y minus negative 7 instead of where y was. So it's always the same for any types of function you're going to deal with in the past or in the future. It's always going to be the same. But why is k not with the value of y? The reason why k is not there is because it is y minus k equals blah blah blah, but you just moved k to the right side of the equation. That's why it's not there, but on the other side. Anyway, the problem with the standard form is that not all the rational functions are already in the standard form, so you have to change the rational functions into the standard format. And how you do that is very simple. You just divide the numerator by denominator. And how you divide a function is quite simple. When you divide a function n of x by d of x, that means that you can express n of x in terms of some sort of number multiplied by d of x plus a remainder. Let's say any constant c. And if you put this value of n of x back into this fraction, it's going to be n of x d of x being equal to k d of x plus c over d of x. And it's obvious that it's always that you can separate the fraction when there's addition in the numerator. So it's going to be k d of x over d of x plus c over d of x. You can cancel it out. Not surprising, I guess. You cancel out d of x, and you keep the latter part. So it's going to result in k plus c over dx. And if you manipulate it a little, it's going to eventually be the standard form you are familiar with. That's it. You just have to divide the numerator by denominator, and you're going to get the standard form. let's tackle how to get the asymptotes and intercepts in the rational functions. That's another important part that you have to know. In case of the vertical asymptote, it's very easy. When you see a rational function, let's say there's x minus 1 and x plus 2 and x minus 4 times 2x minus 2, and it's very obvious that you can simplify 2x minus 2, this part, into 2 times x minus 1, and if you cancel out x minus 1 and x minus 1, the final simplified form is going to be x minus 4 over x plus 2. And you always have to remember that in any fraction, if it's a rational function or some sort of fraction you're going to face in the future, the denominator can never be 0, because when the denominator is 0, it's going to be undefined immediately. And let's try to put any value very close to 0. Let's say it's 0.001, and let's say it's 5. It's a very large number, and as the denominator gets very close to 0, the actual value of the function gets very large. And if this denominator becomes 0, you think that there's going to be a very steep spike in the graph, like this, around this very point where you can't actually have a value. And that's a point where you call a vertical asymptote. How about the value that is cancelled out during the simplification? If you cancelled out a certain expression for the sake of simplification, you shouldn't forget it, because this whole expression, this whole function is the original function, and if you still put 1 and for the value of 1, the denominator becomes 0. That means that you can't put that value of x inside a function, because it's not going to have any value. It's not going to give you any value. But since it's not going to be present, or it's not going to be included in the function after you simplify it, so you just call it an excluded value. And if you graph it, it's actually going to give you a little hole in a graph, and you call it a hole discontinuity. Hole discontinuity. Let's look at the vertical. This is it for the vertical asymptote, and let's have a look at the horizontal asymptote and the slant asymptote. What you have to do to find the slant asymptote and the horizontal asymptote is to compare the order of the numerator and the denominator. There can be 3 cases when the denominator and the numerator are in the same order, or if they have the same exponent. And in this case, the exponents are n for the numerator and m for the denominator. If n and m are the same, you can just look at the coefficient of the numerator and denominator and get the ratio, and that's going to be the horizontal asymptote. Y equals a over b, and that's going to be a straight line where the graph is going to approach infinitely but never going to touch a over b. A over b, yes. The reason why it becomes like this, I'll explain it to you later on. The second case is when the denominator is actually in a higher order than the numerator. You just have to make it 0. You just have to assume, you just can assume that it's 0. And let's have a look. Let's sum up the first 2 cases, because they have the similar explanation. When they have the same order, the horizontal asymptote has a meaning that when x is approaching infinity or getting extremely large, or when getting extremely small. In both cases, when the order when they're in the same order, the denominator and the numerator, you can just assume that the numerator and the denominator is increasing or decreasing in the same rate, and that can help you. They can just make you to disregard the other parts of the function, and only the ratio of the denominator and the numerator is going to remain as a horizontal asymptote. And this is going to be a little easier for you to understand if you know the concept of limit expression. And in case when the denominator has higher order than the numerator, when the value of x gets infinitely small or infinitely large, that's gonna give you a 0 because the denominator is going to get much larger or smaller at a faster rate, and that means that as the denominator gets very large, the value of the actual function gets very small, because you're dividing something with a much larger value that makes the function value to the fraction to be actually very small, and that makes the horizontal asymptote to be 0, or the function to approach 0 infinitely close, but never to touch it. So the last case, when the numerator has higher order than the denominator, this is a case when the horizontal asymptote does not actually appear, because as I said, when the denominator gets much large, the value becomes 0, but what happens when the numerator gets very large? It just approaches infinity. It doesn't have such thing as horizontal asymptote, but you can have something called slant asymptote, only in case when the numerator is only one in order, only one higher than that of the denominator. This again, the division method comes up. You divide p of x, or the numerator, by q of x, and if you get a first order expression or a linear graph, and that's going to be the slant asymptote. That's it. That's it for the horizontal asymptote and the slant asymptote. In case of the y-intercept and x-intercept, it's always the same. When you want to find a y-intercept, you put 0 in the value of x and look for the value of y. Look at the constants and look at the numerators and the denominators. In case of the x-intercept, you have to make y into 0 and look for x. But in this case, since the rational function is a little special form, you can just disregard the denominator. Let's say it's x minus 1 over x plus 2 is equal to 0, which was originally y. In order for you to simplify this, you can just multiply x plus 1 on each side and cancel. 0 times something is always 0, so it's eventually going to tackle only the numerator. So x minus 1 is equal to 0, so the x-intercept is when x is equal to 1. This is very simple, and this is also very convenient because you only have to look at the numerator. And for you to make a better, have a better guess or better shape of the graph, you have to put in easy values between the vertical asymptotes and between vertical asymptotes and intercepts. And if you check all the points, if the graph is going upward or downward, if it's below the horizontal asymptote or above the horizontal asymptote, then you'll be able to start graphing. So addition and subtraction. Find the least common denominator or the least common multiple of the denominators of the two things you're adding up, or more than two sometimes, of the rational functions, and just factor out, get the common denominator, and just add them up. In case of the subtraction, you just do the same thing, but you're subtracting one from another after getting the least common denominator. And always don't forget to simplify. In case of the multiplication and division, you multiply numerators by numerators and multiply denominators to denominators when it's multiplication. And in case of division, it's almost the same, except the fact that you have to flip or reciprocate the divisor, then multiply numerators to numerators and denominators to denominators, and that's it. Oh, for the division, you shouldn't forget the excluded values or the whole discontinuities for both of the things, the thing that you're dividing and the thing that will divide. Look at the excluded value before you do the operation, okay? So let's sum it up. So you have to look at the horizontal asymptote, slant asymptote, vertical asymptote, stretch, intercept, and operations. When you're graphing, I would like to recommend you to just get the horizontal and vertical asymptotes first, put the test values in, and just start graphing right after that. Because when you know that, you don't really have to get the stretch. Personally, I found stretch not really helpful, but it depends on the personal style how you graph it. But for the sake of accuracy, you have to look for the both stretch and the asymptotes and intercepts. But it's just my recommendation. Look for the asymptotes first.